Stefan, we're about to go. They're about to get rowdy. Great. So our next talk is by Avik from IIT Kanpur, and he's going to be talking about differentiable rendering and deep learning. Take it away.
Hey everyone, I'm Avik Pal. So what is rendering? So rendering is basically converting a three-dimensional scene into a two-dimensional projection in the camera space. How we specify the three-dimensional scene, I will talk about it a bit later. But let's start with what is ray tracing. So ray tracing is this particular technique which we use for rendering photorealistic images. However, that's very computationally expensive, and as a result, we generally implement renderers in C++ or low-level languages. These are generally the kind of images which get rendered by ray tracers. So why do we actually need RayTracer? So a RayTracer is basically written completely in Julia. One of the good things about this differentiable RayTracer is that it's a completely general purpose renderer, and we just use Zygote for differentiability. Most of the other renderers that are written and which are differentiable are actually make a lot of special assumptions for it. So basically we can, if you implement any other general renderer and just plug in Zygote, we should be able to calculate the gradients with it. So this is a Duckytown environment which we rendered using RayTracer. So I will talk about Duckytown in a moment, but so we can actually do pretty cool things like photorealistic images with RayTracer as of now. So how do we actually define the 3D object and how is it rendered? So the API is pretty simple. You start with defining the resolution of the screen, and then you load a OBJ file. So OBJ file is basically a file which contains the information about the vertices of the triangles of the scene. We triangulate that and convert it to a form which the RayTracer understands. Then you specify the kind of lighting the scene has. So here I'm just using a single light. You can have as many lights as you want. And finally, you set up your camera. So the camera is basically where the eye is placed. And then you just simply call the RayTrace function, and you get something like this after unpacking the vec3 object which is returned. So how do you get the gradients out of it? So it's pretty simple. You just wrap the entire thing around Zygote, and you just get the gradients. So in this case, we are computing the gradients with respect to light. So let's say I want to compute the gradient with respect to the look from this vec3. So we would just wrap this Zygote.gradient around this origin and the color. So the entire thing just goes inside this, inside the do end block. And you just get the gradients. So there's another interesting problem in computer graphics that is called inverse rendering. So like in rendering, you convert a 3D scene to a 2D image. In inverse rendering, we try to do the exact opposite. We take the 2D image and convert it to the 3D scene parameters. But in itself, it's a very difficult problem because there's an infinite number of possibilities which can happen. So we try to solve a small subset of that problem, which is basically, we assume that we know some of the parameters of the scene. And we know that, so X, Y, Z are the parameters which we don't know. And we simply compute the gradients with respect to that and optimize it. This is the basic way we do it. So we start with an initial guess of the parameters of the scene. Now we render the image. And as I mentioned, we already have the target image which we want to reconstruct. So we compute the mean squared error in the pixel space and just call Zygote and use any other optimization framework like Flux optimizes or Optem to optimize it. So this method works pretty well if you have very few geometric discontinuities in the scene. So for example, if you're trying to optimize the materials of the scene or the lighting parameters, this one will most of the time give you the correct results. So yeah, so here's a small demo. So here we want to reconstruct this target image. And there's an inverse lighting problem. So as I mentioned that we know some of the parameters. So in this case, we know how, so where the vertices are placed in the three-dimensional space where the camera is placed. However, we do not know what is the exact lighting condition. So here here we use Adam and we use Zygote for the gradients, and we are trying to iteratively optimize this image to match the target image. Now finally, let's see about like deep learning. So so Duckytown is basically a test bed for self-driving cars. So it gives us this. So Duckytown has this internally has a scene configuration, and it has a physics engine written in it. It was originally written in Python, but recently it was converted to Julia by Tejan. So how it works is that Duckytown gives us the scene configuration. Like we loaded the OBJ file in a similar format. Duckytown creates, like triangulates the objects, the lighting, and the camera, and gives it to the RayTracer. Now the RayTracer basically generates the image, and it is given to the neural network. The neural network just then outputs the control parameters. So the control parameters are basically the velocity of the car, velocity of the two wheels of the car. And the objective of the car is to stay on the road, move forward, follow a line, and stay alive for the maximum number of time. And this action which the neural network outputs is then finally fed to the physics engine inside Duckytown. And this loop continues, and we keep on computing the reward. So yeah, if we unroll this thing in time, so this is how it works. So this is the forward pass of the algorithm. Now let's go to the backward pass here. So the way we train this thing is, so like Mike mentioned about the Trebuchet model, in which we differentiate through an ODE solver. So in this case, we differentiate through the different RayTracer and the physics engine as well as the scene configuration module. So we have this notion of sub-episodes. So like in reinforcement learning, there is an elongated episode idea. Here we exploit the idea like, so we have an episode, and inside it we have several small episodes, which we actually call sub-episodes. In one sub-episode, we compute this, say there are 5 such rows. So in that case, the length of the sub-episode would be 5. And we would compute the sum of all the rewards into this cumulative reward, and then just backpropagate through the entire pipeline. So why do we actually need the differentiable RayTracer? Is that, say I want to backpropagate this last reward to the first, that neural network. To do that, I actually need to backpropagate through this differentiable RayTracer. Now, what would happen if we could not backpropagate through here? It would just be that the car is just looking at the immediate goal, so it just tries to stay alive for the next time step. But ideally, the objective of the car is to stay alive not for the next time step, but it should optimize its action based on the future rewards as well. So this is what actually helps it, and also this method allows us to shrink the neural network to a very, very small level. And by very, very small, I mean like a 3-layered convolution network, which is really shallow. So this is actually an ongoing project. So we have like very few demos of this, but so we were able to successfully train it on a straight road map and a small loop. So I mean, this loop is clockwise. So, and we also trained it on, tried it out on anti-clockwise, and it actually trains pretty fast. It's like 17 to 18 episodes of training. Yeah, and so the future work. So the main future work would be to incorporate GPU support and multi-threading, and they improve the performance of the backward pass. As for the benchmarks, I do not have the official results, but I tried it on some dummy problems. And there's this Redner software, which is like one of the best ones for differentiable rendering. And it turns out and it's written in C++, and for the forward pass, we are actually by a significant amount, we are faster. And for the backward pass, we are actually at par with it. For TF graphics, I do not have the results because it actually doesn't use a ray tracer. It uses something called rasterization, and yeah. And yeah, thanks to everyone who helped it. Travel grants and Tej and Mike, Dharya, and everyone else. Thank you.
Does anyone have questions?
So, these GPUs have some hardware
Here.
support. We have some hardware support for. Is this something we would have to return?
We can try that. The main issue would be, so do you want us to use the existing live frameworks that exist for RayTracer? Do you?
I mean, the new hardware support for ray tracing.
Yes. So yeah, we can actually use that to make it faster. But if it depends on some foreign calls, like if it's written in C++ or C, something like that, it would be difficult to differentiate through it.